Hey folks, so this is the proof of the weak maximum principle we discussed briefly in class, but didn't actually complete the proof. So as a reminder, we're going to show that if U is a solution to the heat equation on some domain omega, then the weak maximum principle states that the max and the min of U occurs on the parabolic boundary. In other words, the maximum of U considered over just the parabolic boundary is the same thing as considering the max of U over the entire domain. Okay, so as a reminder, the parabolic boundary, remember, is this set omega sub p, which is either the initial condition, right? So when t equals 0, or the left boundary x equals 0, or the right boundary x equals L. So one of those three sides. Okay, so we want to prove that the maximum of U occurs on that set, and everything in the domain is less than or equal to that, basically. So the idea we had, right, was, well, if U attains a max in the interior, then we would have had a contradiction, roughly, right? Because at a maximum, we have first derivatives are 0, second derivatives are negative. Well, if it were strictly negative, we'd have a contradiction to the fact that U solves the heat equation, but because this could be sort of a degenerate case where the second derivative is 0, well, then we don't have a contradiction anymore. We just have 0 equals 0, no issue. So to actually do this proof, okay, we have to do this new construction with V, which I just hinted at in class, but let's go through the entire proof now carefully to show how it actually works. So proof. First, let's set up some notation, some sort of, just reformulation of the theorem statement to make it a little easier to work with. So let's let M be the max over just the parabolic boundary of U. Okay. So I consider all the parabolic boundary, think about what U looks like on all those things, and let's just let M be the max on just those three sides of the domain. So then my goal, right, for my theorem has become to show that in fact, U of x comma t is less than or equal to M for all other points in the domain, right? Because this will show that, yes, U attains its max on the parabolic boundary. Everything else in the interior is less than or equal to it, okay? So the max over the whole thing would have been enough to just look at the parabolic boundary. Okay, so how do I show this? Well, so this is where we construct our new function. So consider the new function v of xt, which is U plus epsilon times x squared. Okay, so here epsilon is some positive real number. And okay, so what do we need to do here? So some things that we want to think about are that v, this new function, okay, it doesn't actually solve the heat equation. We have to be careful about that, right? Because it's a new function. There's no guarantee it solves the same PDE that you did. But the point of adding this epsilon x squared, right? The point of this little addition is to force away, right, this possibility of sort of degenerate second derivatives, right? X squared is truly, you might say, like strictly concave, right? It doesn't have second derivative equals 0 at that minimum. So this will help get rid of that issue that plagued us before. Okay, but let's see like how this actually works. So the first thing to do is realize that V, it's a different function. So like we have to sort of think about it separately. So there's no guarantee that V also has maximum M, right? I mean, on the parabolic boundary. So let's recompute what do we know about V on the parabolic boundary. So what is the max of V of xt over the parabolic boundary? Well, we can plug back in the expression U of xt plus epsilon x squared. And now we'll use a general fact that's true about maxima. So first, let me write down the fact, and then we'll dissect why this makes sense. So this is less than the max over the parabolic boundary of U plus the max over the parabolic boundary of epsilon x squared. Now, why is that true? So this inequality happens because, so the max on the left-hand side is find the x and the t which makes this sum as big as possible. But importantly, I have to use the same x for the u and for the x squared. On the right-hand side, what I'm saying is, well, let me separate these two and take the max of each part separately. So now potentially I have different x's for the u of x t and the x squared. So of course, the expression on the right can only be bigger than what was on the left, right? Because I have a little more freedom to choose two different x's. So that's an inequality. And then this is not equal, but less than or equal to. Oh no, actually it is equal to, sorry. It is equal to. So the max of the parabolic boundary of u, we said before, is denoted by m plus, and now we ask what's the maximum of this function epsilon x squared? Well, x we know is between 0 and L. So the biggest that can be is just L. So particularly epsilon L squared. Okay. So what we've shown in total, right, is V on the parabolic boundary is not bounded by M, it's actually bounded by M plus epsilon L squared. Okay, again, where L is the length of the space interval. Fine. So now let's consider why V actually can't be bigger than this quantity, not just on the parabolic boundary, but actually on the entire domain. So let's do a short contradiction here. So let's assume to the contrary that there exists some point x naught t naught somewhere in my domain, right? Not just the parabolic boundary, but anywhere in the domain, such that V of x naught t naught is a global max. Meaning, right, it's truly a global max, and actually it's bigger than this m plus epsilon L squared, right? So like I'm assuming that I can beat this maximum somewhere in the domain that I wrote before. And so just like before now, so like if this truly is a global max, then the same computations we did before hold. So we know at a global max, the first derivative should be 0. The second derivative should be less than or equal to 0. Again, using sort of first derivative, no, just like the properties of first derivatives and then sort of second derivative test looking things. So now we'd be careful, right? Because you can't say, well, Vt equals kvxx. So right, again, we don't know V solves the heat equation, so we can't actually write that down. But instead, what we can do is then say, well, let's consider not the heat equation, but just this expression Vt minus kvxx, right? If V were a solution to the heat equation, this would be 0, but we actually don't know that, right? So let's just manipulate this thing and see what it looks like. So from what we just wrote, so Vt minus kvxx is, well, using the inequalities and equalities I just wrote down, this is 0 minus something that is less than or equal to 0, right? So something not positive. So 0 minus a not positive thing. So at the end of the day, I'm getting a positive thing here, right? So this result needs to be bigger than or equal to 0. Okay. Fine. But on the other hand, so right now we don't have any contradiction, right? But on the other hand, let's plug in our expression. V is u plus epsilon x squared. And so I can calculate Vt equals ut plus 0, time derivative, right, of x squared is 0. And then Vx is ux plus 2 epsilon x. And then Vxx would be uxx plus 2 epsilon. Okay. And so now redoing my Vt minus kvxx, now plugging in the u's, right? Vt is ut minus k times uxx plus 2 epsilon. And so that would be ut minus kuxx minus 2k epsilon. Now, here's where the magic happens. Oops, that's not what I wanted. So this expression, ut minus kuxx, that is indeed exactly 0 because we know u solves the heat equation. V doesn't, but u does. So this expression zeroes out, and all I'm left with is the number negative 2k epsilon. Now we know k is positive, we know epsilon is positive, so this is strictly less than 0. But that is a problem, right? So somehow we have, on the one hand, this expression Vt minus kvxx is bigger than or equal to 0. On the other hand, it's strictly less than 0. So this is a contradiction. This is what adding the epsilon x squared gave us, right? It gave us this little contradiction, okay? So contradiction. And what do we contradict? We contradicted the assumption that I had a global max, right? So contradiction, thus, V of x naught t naught cannot be a maximum at any interior point of omega. And specifically, right, I mean global maximum. I really mean it can't be a global maximum. So because of that, what we've just proved is, yes, V is maximal only on the parabolic boundary. Okay, so that is V of xt is less than or equal to what we said before, right? So before we said it's less than this upper bound on the parabolic boundary. And in fact, now we know it's less than this upper bound for all points x and t, not just on the parabolic boundary, but even in the interior, on the whole domain, this inequality is true. Okay, so all this work is to show that V sort of has this maximum principle that we were hoping for, right? So V is bounded above by this number for all points. Finally, plugging back in U, V was what? U of xt plus epsilon x squared less than or equal to m plus epsilon L squared. And now just for convenience, I'll rearrange to say U is less than m plus epsilon times L squared minus x squared. Again, this is true for all points in the domain. Moreover, this is true for any epsilon bigger than 0. Everything I just did was for an arbitrary epsilon, as long as it was positive. And so this inequality is true no matter what epsilon I take. So by taking the limit as epsilon passes back to 0, we get U of xt is less than or equal to just m. But that is exactly, why'd that happen? That is exactly what I hope to show, right? So if you go back to way beginning, we had said that m was the maximum of U on the parabolic boundary. Our goal was to prove that U was less than m for all points in the domain. And that's finally what we concluded at the end. Thus, we are done. Okay, so really beautiful idea of a proof here. Again, sort of the way I like to think about this in summary is we wanted to show the maximum principle for U, but it was difficult because of this like second derivative sort of degeneracy. And so what we do is introduce this new function V, which is close by to U. Now, the trade-off is V is no longer a solution to the heat equation, but it's kind of close to it, right? So that's what happened in here. And the upside, though, is although we lose that it's no longer a solution to the heat equation, we do gain that it doesn't have the second derivative degeneracy, right? We added sort of a strictly concave function that makes sure that we, don't run into that same sort of like, well, borderline case that we had before. So we are able to prove the maximum principal for V and then pass the limit back to U afterwards. So it's a very beautiful idea of, introduce this new function, prove something true about that, and then take the limit back to the original function. It's a very nice sort of analytical technique. Okay, so hopefully you found this interesting. If you have any questions about the proof, please let me know. And otherwise, I'll see you in class.